My name is, My name is Sakura Pasquarelli. So I will say a few words about myself. So I'm Italian. Why is everybody laughing? For my name? Well, my first name is Japanese because I was born in Japan. So that's Sakura is a Japanese name. So I was born in Japan. I lived many years in Asia. I grew up actually in Asia, in Burma, Indonesia. And when I was 16 years old, I went back to Italy. And I went to university in Rome, La Sapienza. And then after university, I had a scholarship at the National Institute for Nuclear Physics in Frascati, very close to Rome. And that's when I started being acquainted with synchrotron radiation. I was in a group that was planning the Italian beamline at the European synchrotron. This was in the late 80s, and the European synchrotron didn't exist yet, but I was already starting to work on, the design, optical design. And then in 1993, I was sent here to Grenoble I was the person of the group who was here. I didn't have a family. I was the youngest one. And so they just sent me, and I was in charge of, making sure that things went on, and the beamline was built, and then we commissioned it. And then I was recruited by the SRF as scientist on another beamline, and I did my whole career at the SRF. I was here for 26 years. So I became group head. And then last year, I left the SRF. I left France, and my family is here, and I went to Hamburg. So I'm now at the European XFEL. I'm scientific director there, and since 1 year. And so I will be there for a few years, and then we'll see. But I want you to know that 30 years ago, I was in this room, just like you, following Hercules. In 1991, it was the first Hercules course ever organized, and I was one of you. I was one of the students. And at that time, things weren't as organized as they are now. So we were staying here for 6 weeks, in February. It was very cold. And in France, you have the school holidays in this period. So everybody goes skiing, and the schools were closed. And we were staying on the last floor of a lycée Mounier, in the middle of Grenoble. And when the school holidays started, so we were staying on the last floor, we were sleeping there, and there were little kitchens. We didn't have nice fancy hotels like you have today. And when the holidays started, they switched off the heating. so we were freezing to death in our rooms. Anyway, so 30 years have gone by, and things are much better for you now. So what are we going to do today? We're going to talk, the first 45 minutes roughly, we're going to talk about, it's going to be a general introduction to X-ray spectroscopies. And then I will focus more on X-ray absorption spectroscopy, and in particular, extended X-ray absorption fine structure spectroscopy. So this is a little bit what we're going to do. So I'm going to start very, very generally. So if you have questions, of course, you can stop me, but we will have regular interruptions, so you can come and ask me more questions. So as you can see here, going very, very, very slowly at the beginning. So the idea is to get all of you on board. So this first part will be sort of hand waving, quite simple, so that everybody follows. I would like to know how many of you here are already involved in this kind of techniques. I mean, EXAFS, absorption spectroscopy. Not many, actually. Okay, a few of you. And how many of you have a background that does not include quantum mechanics? Okay, a little bit. So most of you do. Okay, it's just because EXAFS is a quantum mechanical phenomena. So it's difficult to really, really understand if you do not have the math background. But I have found a way to get around this. Okay, and we will see if it works. So there will be a little bit of math, but very little. Okay, so we start this introduction. So I'm going to start from the beginning. So X-ray matter interaction and different families of experimental techniques. So when we have X-rays, I indicate here the energy, h bar omega. Omega is the frequency of the electromagnetic field. I0 is the number of photons that arrive on a sample. So when you have photons arriving on the sample, many things can happen to these photons. So you can have photons that disappear. Okay, so that means that if you put a detector here, you measure less photons than what came in. But you can measure less photons here because they have been diffused somewhere else. So we call that scattering. Okay, so they can go somewhere else because they're scattered, and in this process they can maintain their initial energy, so that is elastic scattering, or they can lose energy in the sample, and that's inelastic scattering. As I said, they can be transmitted or they can disappear. Actually, they're nowhere, they're gone. But you can also see not only photons coming out of the sample, but you can also measure electrons, for example. So you can produce electrons. So many, many things can happen. Now, we distinguish two fundamental, all these interactions can be split into two fundamental areas. One is photoelectric absorption, and these are the cases where the photon actually disappears. And here we have scattering interactions. That means the photon is still there. It has either maintained its energy or it has lost some energy. So these are the two fundamental X-ray matter interactions. Okay, so as I said, those are the two interactions. And then we have two different families of experimental techniques. One family covers all kinds of elastic scattering, and the other family covers what we call spectroscopic techniques, and these include photoelectric absorption and inelastic scattering. Okay? So here we have all phenomena where you have no exchange of energy between the photons and the sample. And so here you're looking mainly at the microscopic geometric structure, and you have done, I think, already a few lessons on this. And we talk about diffraction when we're looking at periodic systems, and we generally talk about just scattering when we're looking at disordered systems like liquids or amorphous systems, and so on and so forth. And these are some of the acronyms that you have seen. So X-ray diffraction, grazing incidence X-ray diffraction, this is all ordered systems. And here we have X-ray scattering, wide-angle X-ray scattering, small-angle X-ray scattering. This is in general things that don't have a long-range order. For spectroscopy, these are all phenomena where you do have an exchange of energy between the photon and your system. And here you get information on the electronic structure, on the local structure, and on the dynamics of what's happening in the sample. And so here we have techniques such as X-ray absorption spectroscopy, EXAFS, XANES, etc. We have emission spectroscopy, photoelectron spectroscopy, and also inelastic scattering, because also here, even though it's called scattering, it's inelastic, so you're exchanging energy. And so you see acronyms such as inelastic X-ray scattering, resident inelastic X-ray scattering. We will see a little bit of all this. So this is a spectrum of inelastic scattered photons. Just to show you that we do spectroscopy by looking at inelastically scattered photons. They give you information on the different excitations that can occur in a sample. So for example, you see here, this is the energy transferred into the, I'm still getting confused with these buttons. This is the energy transferred to the solid. So here, this would be the elastic peak, and these tails are the quasi-elastic photons. So these are those that have almost lost nothing. Then you have here photons that have lost very little, a few milli-electron volts, because they have excited, excitations in the sample like phonons, magnons, and so on and so forth. A little bit higher here, we're looking at valence electrons, a few electron volts, and so on and so forth. Core electrons, and then at the end you have all photons that have lost almost everything, and this is a big, big tail called the Compton tail. So you see it's inelastic scattering, but this gives you spectroscopic information. There's going to be a lecture on this by Mikkel Krisch on the 2nd of April, so we're not going to cover this too much. So we go back to the picture that we saw initially, and you see here I'm just putting some tags on all these different phenomena, and we will be looking in this very brief overview at X-ray absorption spectroscopy, X-ray emission spectroscopy, and photoelectron spectroscopy, mainly. A little bit of inelastic scattering. So, start from X-ray absorption spectroscopy, the basic principles. So in X-ray absorption spectroscopy, you want to measure the absorption coefficient that we call mu. You want to measure mu as a function of energy of the incoming photons. So you have a sample, thickness T. You have an incoming flux, so this is the number of photons that arrive on the sample per unit time. And then you have a flux I, which is the transmitted flux. And this is the definition of absorption coefficient. It's just this very simple exponential. So you define it like this, through this exponential. I, transmitted flux, is equal to the incident flux multiplied by e to the minus mu t. So mu is the linear absorption coefficient, and it has units, dimensions to the minus 1. So if t you put millimeters, then mu will be millimeters to the minus 1. If it's centimeters to the minus 1. And so that's the way you calculate it here. Now, how do we measure it? So if you want to measure mu over a large energy range, you need an X-ray source with many energies. So typically you go to a synchrotron, and I think you have had a little bit of background on the kind of sources that we have here. A bending magnet, for example, produces a very broad energy range in the spectrum, and so you go to a bending magnet. You use a monochromator because you want to select one energy, and then you measure the incident flux before the sample and after the sample at that energy. Then you change the energy, so you change the monochromator angle, and you do again. You measure I0 and I, and so on and so forth for every point. That's how we do it. Okay, and then you calculate this, this quantity as the logarithm of I0 over I. So this is what typical absorption coefficients look like for a few elements. And this is a log-log plot. Okay, so pay attention. This is energy in kiloelectron volts from 1 to 100. And these are the values of the absorption coefficient. This is normalized by the density so that we can put everything more or less together. So what do we see here? We see that mu depends very strongly on the energy. It decreases. This is decreasing, very strongly decreasing function because this is a log-log plot. It depends on the atomic number. Okay, so you have oxygen here in black, you have lead in blue. Obviously depends also on the density and on the atomic mass. So you see here we have some elements that have no jump and other elements that have jumps. But these jumps are at specific energies that are characteristic of the element. Okay, so this is what we call the absorption edges, these jumps that you see here. So for example, oxygen doesn't have any absorption edge between 1 keV and 100. Iron has 1, cadmium has several, and so on and so forth. The heavier the element, the more absorption edges you see. And one thing is, you have to notice this, as you go to high energies, the absorption coefficient really goes to 0. This is telling us that when you go to very high X-ray energies, everything becomes transparent to X-rays. Absorption goes to 0. Now, if we take one element, let's take, for example, germanium, and we look at this a little bit more closely. We look at the absorption coefficient, which is shown here on the top. And then, so this is calculated as I showed you before. It's the log of I0 over I, which means that you're actually including in this quantity every single thing that makes it that you have lost photons in I. Okay? That means all the phenomena that we mentioned at the beginning are in principle in this definition. They're counted, right? Because you're measuring I. So whether these photons are not there because they have been elastically scattered or because they have been inelastically scattered somewhere else, so they're no longer behind the sample, or because they have been absorbed, that means that they do not exist anymore, nowhere, it's all in there. So you see, these are the different contributions. You have, this is the total absorption coefficient on the top, and then you have here, this is the contribution to the total absorption coefficient coming only from photoelectric absorption. This is the contribution coming from elastic scattering, and this is the contribution coming from inelastic scattering. So what you see here in this plot, what the important message is that in this energy range from 100 to about 10,000, 100,000 eV, the main contribution to the absorption coefficient comes from photoelectric absorption. So this is the phenomena which is the most probable. So from now on, we will forget about everything else for X-ray absorption spectroscopy, and we will focus just on photoelectric absorption. So it dominates the absorption coefficient in this energy range. And this is the energy range where we work at. This is where all the edges are, as you saw previously. So what is photoelectric absorption? Well, it's a process by which you have X-rays, okay, that come in, and they can be absorbed. And when I say absorbed, that means they disappear. They're absorbed by matter through the photoelectric effect. So the photoelectric effect is you have an X-ray that has sufficient energy to free a core electron in one of the atoms in your sample. So these are electrons that are tightly bound to the nucleus. They have a binding energy. If the X-ray has sufficient energy, that means higher, more than the binding energy, the electron can be freed. Okay, so it's kicked out of the atom, and from then on, we call this electron the photoelectron. So remember this, because we're going to be talking about the photoelectron a lot today. So this is a very, very important particle. So after this process has occurred, the atom is in an excited state because there is a hole here, right? An absence of a negative charge. And this changes a little bit things, right? The atom finds itself in an excited state. So it wants to go back very quickly to its ground state. And so it wants to de-excite itself. And this can occur through different channels. You can have either radiative de-excitation or non-radiative de-excitation. In radiative de-excitation, the hole is filled by an external electron that jumps in, fills the hole, and the excess energy is released by emitting photons. So this is what we mean by radiative de-excitation. The atom radiates, and these are the photons. Now, if you're able to measure the energies of these photons, they give you information on, the exact energies depend on the exact, let's say, transitions that have occurred. So they tell you what kind of absorber, what is the element that has absorbed, where the core hole was, and it tells you also which transition has occurred. Okay, so they give you a lot of information. Non-radiative is very similar, so you have an external electron that fills the hole, but the excess energy is released through the emission of another electron that we call Auger electron. And here again, if we can measure the energy of that electron, the Auger electron, we get information on who was the photoabsorber to start with, where was the core hole, and what are the transitions that are involved. Okay. So we've already seen this picture again, but I've added a detector here. Okay, so before we had only I0 and I, and now we've added this detector because actually you can do the measurement of the absorption coefficient either by measuring the transmitted intensity, and you use this formula that we've already seen, okay? And this is the only exact measurement of the absorption coefficient. So every time that you can do a transmission measurement, you should do a transmission measurement because it's the only one that will give you exactly the absorption coefficient. Everything else is an approximation. But very often we cannot use transmission, either because sometimes our samples are too thick, so you measure nothing in the back, right? And you cannot make them thinner. Or sometimes the samples are really, really dilute. So what absorbs is really, the edge is really, really small. The contrast at the absorption edge is so small that you cannot really use a transmission measurement. So in many, many cases, we cannot use this transmission measurement. And so what we look at is the processes, the de-excitation processes, radiative or non-radiative. So if we look at, for example, a radiative de-excitation process, we measure the fluorescence that comes out during this filling of the core hole. So we're measuring that process, which is proportional, of course, to the full holes that you have created. Okay? But it's not directly the absorption coefficient. In some cases, the approximations work well. In some cases, they don't. So you always have to ask yourself the question. So here it's just a pictorial view to see the process. So you see we have here schematics of the atom. So we typically say that we're looking at the K edges when we're exciting a 1s electron. We call the L edges when we're exciting a 2p electron, an electron from a, typically a 2p electron. And here you have the energies of the K edges and the energies of the edges. Okay, so these are schematically the transitions that we're looking at. So very often you see these graphs. And so you see the K edges go from typically what we can do here at the SRF. On typical bending magnets, you cover, something like from between 4 keV up to 80 keV, because the SRF is a high energy synchrotron, and therefore we can go to pretty high energies on these bending magnets. And then we have access also to a lot of the L edges. So the characteristics are of X-ray absorption spectroscopy, the element selectivity, because if you can measure the energy at which you have the edge, you know what atom has absorbed the photon. Chemical sensitivity, because as you will see, the exact position of this edge and the details of the shape of this absorption edge depend on the chemical state of the element. And we will see this later. Spin selectivity, because you will see also that the absorption coefficient is different if you use circularly polarized X-rays of one or another helicity. So you get information on spin. Also, if you're looking at photons, so for example, you're looking at transmission, you're measuring I, the transmitted photons, or if you're looking at fluorescence and therefore you're measuring photons again, you get bulk sensitivity, so microns. If you're measuring electrons from a de-excitation process, you're sensitive to the surface because electrons have a very short mean free path in solids. So I'm talking here about less than 100 angstroms, depending on the energy of these photoelectrons. It can be of course, much more, but typically these are the values. And then of course you have spatial selectivity, because now we use a lot of imaging techniques. So we can focus these beams, we can use full field techniques, and you will have also some, I think, lessons on imaging. Okay, so that was general introduction to X-ray absorption spectroscopy. Any questions on this part?
So
yeah?
What we actually measure in fluorescence mode, is it also absorption coefficient?
Yes, yes, but it's not exactly the absorption coefficient. If you have a sample which is very dilute, then you're measuring something which is very close to the absorption coefficient. If you're measuring a sample which is concentrated, the fluorescence photons that you produce when the atoms de-excite can be reabsorbed before leaving the sample. So you measure something which is distorted, and it depends also on the angle where you are, where you put your detector. You see, because imagine you have a sample that is like this. You send the beam like this. So the beam excites everything from here to here, the whole bulk. And then you put your detector here. So the atoms that are here, right, will produce fluorescence photons that if they have to reach the detector, they're going to have to go like this. They're going through the sample, but not very much. But those that are here are going to have to cross the whole sample. So they will be reabsorbed. You see? So it's not a direct measurement. It's a measurement that works if you have certain conditions. For example, if your sample is very dilute, then it's okay, because the probability of this photon being reabsorbed is very, very low. Okay?
Sorry.
Yeah?
I have a question. Considering that you can have a sample with different elements,
Yeah?
once you have an incident beam with X energy,
Yeah?
which is higher than the energy for exciting a lighter element.
Yeah?
What happened to all this absorption? Because of course you can have absorption.
Of course. If you have a photon, for example, that is 10 keV, and you go on a sample which has silicon, magnesium, iron, and all this, of course, this photon can excite all of these atoms, all of them, right? So you will have, but I mean, the probability, you will be scanning a certain range, and you will be looking at the energy of interest. But if, let's say you're looking at iron, you will see a nice edge at 7.1 keV. But if you can move your monochromator and go and scan at silicon, you will also see an edge at silicon. But normally you don't go very far. You focus on one element. Other questions? Okay, we go on. So now, I want to focus a little bit more on X-ray absorption fine structure. This is in the framework of this general introduction, and then we will go back on this a lot later on. So I'm going to go a little bit quickly. So what is X-ray absorption fine structure? That maybe you have seen this acronym very often. Well, this fine structure refers to these wiggles that appear on top of an absorption edge, just after the edge. You see all these wiggles. And they are due to the presence of neighbor atoms around the absorber atom. We will see how this works later. So, XAFS usually is broken in two different regimes. The regime close to the edge, which we call XANES, which stands for X-ray absorption near edge spectroscopy, and EXAFS, which is this part, the extended part, X-ray absorption fine structure. So all these little wiggles here. So these two regions, why do we split the two? It's because simply we cannot interpret these features with the same theoretical model. Okay, and I'm going to try and explain why. So that's why we split these two regions, because we can actually use some approximations in this region that allow us to have a very, very simple model of these oscillations that link the frequency of these oscillations, the amplitude, to the number of atoms in the environment, the distance of these atoms with respect to the absorber, and it's pretty simple and it works very well. We can do it in the EXAFS region because we can use some approximations that we cannot use in this region. So this part is much more difficult to analyze. So here we're looking at transitions to unfilled bound states, nearly bound states, and the continuum, right? Because the photon, the photoelectron is excited, and then if the photon has just this energy, the photoelectron will be freed, but it will not have any kinetic energy. It will just sit there, right? If the photon has this energy, then the photoelectron will be kicked out, and then it will have 1,000 eV of kinetic energy. So it will be a pretty high energy particle. A lot of kinetic energy to move around, right? So here we have very low kinetic energy photoelectrons, whereas here we have very high photoelectron kinetic energies. That's the main difference, and we will see why this makes these regions so different. So low energy photoelectrons, high energy photoelectrons. Just remember this, yeah?
So in this case, you don't measure any fluorescence, you measure immediately the electrons that get excited.
No, sorry. Yeah, we're not measuring the photoelectrons. I'm just saying, in the process, you're producing photoelectrons. What we're measuring here is always, at the moment, I mean, you can measure, of course, electrons, photons, whatever you want. But just forget now a little bit about what you're measuring. Just think about the process. You have a photon coming in. It creates holes. And when it creates holes, you have this electron that first was sitting in the 1s position. And now it has become a free electron wandering around in the sample. Okay? At the moment, that's the process. What I measure here is mu, absorption coefficient, which just imagine it as logarithm of I0 over I for the moment, right? It's just a function that you measure by measuring the photons after the sample, for example. But the same, you would get, as I said, you can get practically the same information by measuring the fluorescence in certain cases. Okay, so this is a very important plot. It shows you the inelastic mean free path of electrons in solids. So this tells you that if you have, so as I said, we have produced a photoelectron, which is wandering around in your sample. If the photoelectron has a very small kinetic energy, so you're very close to the edge, low kinetic energy, you see the mean free path can be very long. It can be 100 angstroms, which means that this photoelectron can travel a lot before losing energy. On the other hand, if you are far from the edge, let's say I'm at 1,000 eV from the edge, that means that the photoelectron that I have created, I have freed it, and I have also given the photoelectron a lot of kinetic energy. So I'm here. And you see here, electrons do not travel very much. Their inelastic mean free path in solids is very low. It's a few 5 to 10 angstroms. It's very, very low. That means that these photoelectrons will not travel much. So remember this. So approximations can be used to interpret the EXAFS that are not valid for the XANES. And the approximation depends on the fact that we have different photoelectrons which behave differently, and we will see why this is the case later. So we cannot analyze them in the same way, and they also contain different information content. So in the Xanes region, we're typically looking at local site symmetry, the charge state, and the orbital occupancy. We're very sensitive to the charge and to the details of the potential because the photoelectron has a very low energy. And so any little change in the potential, like even a few eV, will strongly affect this photoelectron because it's about the same energy that he has, right? Here in the EXAFS region, we will be more sensitive to the local structure, and this is something that we will spend some time on later to show you how you get this information. Okay, now I'm going to go quickly through the other core hole spectroscopies. In 10 minutes, we have to stop, right? For a little pause. Okay. So other core hole spectroscopies. So I'm going to go quickly through these other acronyms: emission, resonant inelastic scattering, X-ray Raman. So you see there's a whole zoo of possible core hole spectroscopies. All these techniques have in common that you start from the creation of a core hole. So now you know what this is. The photon is absorbed and you create this core hole. The atom is in an excited state because of the presence of this core hole. And then you can have different kinds of absorption spectroscopy. You can have emission spectroscopies, inelastic X-ray scattering that are related to emission spectroscopies, and I'm going to show you a few of these. There will be, as I said, again, a talk by Mikhail Krish on inelastic scattering, and that is going to also give you more information on this method. So, common to all of these spectroscopies is a concept of transition probability. So I think that you have to, let's say, understand this now. So when we talk about absorption coefficient that we're plotting here, you can also see this as the probability of the photon being absorbed. So every time that you see here absorption coefficient, you can just replace that with probability of the photon being absorbed. Okay? So from a quantum mechanics perspective, this absorption coefficient reflects the probability of a transition from an initial state to a final state. The initial state includes the photon, because the photon is there at the beginning, which has a certain, let's say, polarization direction, that's fine. And it also has a core hole. This is your initial state, and we define, let's say, write it like this. Okay, this is our formalism. It's the I is for initial state. The final state, you see the photon is no longer there, it's disappeared, but we have a photoelectron and we have a core hole. And we indicate it with this little symbol here. And this is a little picture which shows you our initial state. We have a photon, we have an electron. And here we have a core hole and we have a photoelectron. And so what we're measuring here is the probability that we go from this initial state to this final state. Now, we typically write the probability as the sum of all the possible transitions from this initial state to all the possible final states. There can be many final states, right? You can go to many different levels, etc. So typically, the absorption coefficient is the sum over all these transition probabilities. And in quantum mechanics, we write it like this. So you should, those of you who have not done quantum mechanics should not be scared about this, because I will explain to you what this is. But this is what we call transition probability from initial state to final state. So what do we have here? We have here an operator, which is the interaction that causes the transition. Okay, so this is the electromagnetic field atom interaction Hamiltonian operator. It's just an operator that causes the transition. When the photon comes, interacts with the atom, and causes this transition. This operator acts on the initial state and then does something to it. Okay, and if it transforms this initial state into exactly this final state, then you have the probability of this occurring, which is equal to 1. If it transforms this to something else, which is not this final state, then this will be equal to 0, or it will be a very small number. We'll see this a little bit better later. So this is what we call the matrix element of Hi between the initial and the final state. And then you also have the density of final states, because of course you cannot go to any final state, but you have to go to a final state which conserves the energy. There will be a lesson which will go much more into depth in the theory of absorption, of X-ray absorption spectroscopy on the 31st of March. So this is my little, how do you say, refresher for quantum mechanics. So those of you who have not done anything, this is just remember a few things. That in quantum mechanics we use this concept of wave function, which tells us a little bit where this the electron is. So it gives us let's say the probability amplitude of finding an electron at a certain position at a certain time. Now we forget about the time coordinate. We only concentrate on the position. And so you see this is our initial state wave function. It's a complex number, so this is the complex conjugate. We just flip the arrow around. This is the same for the final state. We just show it like this. Now, the modulus square of this quantity is the probability density. What does this mean? That means that if I integrate this function over all space, I get 1. Because if the electron exists, it must exist somewhere in space. I don't know where it is, but if I integrate over all space, I get 1 because it's there. Okay, so this is what it says. And so this notation of matrix element, as I said before, this actually stands for this integral over all space of these three functions, the product of these three functions. So you see, if the operator acts on the initial state to transform this initial state into something which is very similar to this, this integral of psi f multiplied by psi f is equal to 1. Just so that you understand a little bit why we use these matrix elements. Okay, so we're back to our matrix element here, and I have to say a few things about this before maybe we stop. So the consequences of having the fact that the absorption coefficient can be written as a sum over, let's say, all these transition probabilities. There are three main consequences that I'm going to go through quickly. One is that you see there is a final state here, and we cannot determine exactly the energy of this final state. Because remember, in the final state, we have a core hole. And the core hole does not live forever. So due to Heisenberg's indetermination principle, since this core hole does not live forever, I cannot have a very exact evaluation of the energy. So the uncertainty that I have on the energy of the final state is linked to the uncertainty that I have on the energy of the core hole. So this is one thing. That means that if we look at a spectrum, there will be an intrinsic uncertainty on the energies that I measure. I cannot measure them perfectly. And these are typically the intrinsic, let's say, uncertainties that we have. It's what we call the core hole broadening. So this is something that affects all these kinds of spectroscopies. The other thing is that many of these final states will cancel out. We will see this later. And this is what we call the dipole selection rules. Only some of these matrix elements are different from 0. Okay? In particular, if you're looking at a K-edge, the only matrix elements that are different from 0 are those that take the state, let's say a state L equals 0, so we're looking at one s electron, into a state of symmetry P, L equal 1. Okay? All the others are 0. For the L edges, it will be states that go from transitions that take a 2p state, L equal 1, to a state which can be either L equal 0 or L equal 2, and so on and so forth. But we will see this a little bit later. And the last thing is that the absorption coefficient, as you can see, depends on epsilon, which is the polarization of the X-rays. So this is important also, because this allows you to have contrast with different polarizations, so-called X-ray dichroism. Okay, just a little word on spectral broadening. As I said, so we have this spectral broadening, which comes from the fact that the core hole doesn't live forever, right? So delta E times delta T is more or less a constant. And you also have another source of broadening, which is the instrumental broadening that comes from the fact that the incoming beam has a certain divergence when it hits the monochromator, and therefore the resolution will be limited by this divergence. And also, of course, the choice of your crystals, your monochromator crystals. So this is an instrumental broadening. And so you see, for example, here we're looking at the K edge of nickel in nickel oxide using an X-ray tube, which is the blue curve, and at the synchrotron. So you see at the synchrotron you have a much better energy resolution because the divergence of the synchrotron is much smaller. So we're reducing enormously the instrumental resolution. Okay, so when we talk about spectroscopy, this is a concept that you really have to be familiar with. Here we're looking at the L23 edges of nickel in nickel oxide, and you can see here that they're much sharper. And you see this is because when you compare the L edges to the K edges, you see that the core hole is much smaller. It gives a much smaller contribution. Okay, because the lifetime of these core holes is longer than the lifetime of those core holes. So this is the intrinsic resolution, which is smaller for the L edges. Okay, so let's just quickly go through this cartoon. So we've already seen this, X-ray absorption spectroscopy. You excite a core level, it becomes photoelectron, and you are sensitive to the electronic structure in the Xanes region, and we're sensitive to the local structure, as we will see later, in the extended region. Emission spectroscopy. So emission spectroscopies, what we're measuring here is the de-excitation of the atom, right? To go back to the ground state, and we're looking at the photons that are emitted. So if we can measure the energies of these photons, we get information on the transitions and on the atom that has absorbed the photon. Emission and absorption spectroscopy are very complementary because you see, emission spectroscopy is sensitive to the occupied states. It's looking at the density of occupied states, whereas absorption spectroscopy is sensitive to the density of unoccupied states because the transition will not occur if you don't have an available state to host the photoelectron. So they're extremely complementary. In emission spectroscopy, if you're able to analyze the energies of these peaks, then you can get information on the ligands, for example, the chemical state of the absorber, and also on the spin state, valence band spin state. This is an example. So we're looking here at K beta emission. So these are different emission lines. So you have K alpha is when you have a transition from a 2p to fill the hole. It's called K alpha. K beta is when you're filling the hole with a 3p electron, and then you have valence to core transitions, which are very, very small, that are direct transitions from the valence band to fill the core hole. So K beta emission is a very common technique that is used because it's very sensitive to the valence band spin state. So for example, this is K beta on different manganese complexes. So you see, we go from a manganese complex MnF2, which has a very high spin, so you have 5 electrons in the 5D state, to a complex which has a much smaller spin, and you see how the spectrum changes. So when you go from high spin to low spin, this little satellite, also called K beta prime, goes down, and this peak slightly shifts. So we have the sensitivity to spin. Why? Because the energy levels of the 3p are strongly affected by how many spins you have in the 3D. Okay? There is an interaction between these levels, and therefore you can get information on the spins through this spectroscopy. I think we stop here for a few minutes, and then we continue. If you have any questions, I'm happy to answer them. We do 5 minutes break. We started going through the different core hole spectroscopies. We went quickly through X-ray absorption spectroscopy. Now we went through emission spectroscopy, and I showed you the example of K beta emission, which is sensitive to the spin state of the valence band. And now we go to resonant X-ray emission. So what I showed you before is called non-resonant. Resonant is the case where the incident photon is very close to an absorption edge. Okay? So when the incident photon is very close to an absorption edge, the absorption process and the emission process can no longer be treated independently. They become dependent on each other. So the emission, how many photons are emitted, depends on the energy of the incoming photon. Right? So in this case, the two processes are linked. So here I'm going to show you an example of the resonant X-ray emission spectroscopy on a 3D transition metal. So we also call this resonant inelastic X-ray scattering, RIX. So you have a photon coming in. So as I said, the energy of this photon is very close to an absorption edge. So you have a core hole which is created, and you're just at the edge. So you see this transition goes from 1s to 3D. It fills an available, let's see, an available hole in the valence band. So look at this. This is the final state of absorption spectroscopy. You're just at the edge, so you don't have enough energy to go to the continuum, but you're just right there. So this is the final state of a K absorption edge in a 3D metal. But then what happens is that you have, for example, a 2p electron that fills this hole, and you have emission of a photon. So look at this state. This final state corresponds to the final state of the process whereby you're absorbing a photon that takes a 2p electron to a 3D state. So this is the soft X-ray absorption spectrum in these systems. This is an L-edge final state. This is a K-edge final state. You have a hole here. This is an L-edge final state because you have a hole here. Okay? So actually, when you do resonant emission spectroscopy, the final state corresponds to this final state that you have in the L-edge. So it's as if you're doing soft X-ray absorption, but using a high energy photon. So this is interesting because this final state has a much smaller spectral broadening, okay, because it's an L-edge. Remember, I showed this before to you. The core hole here lives much longer, so you have much sharper features. So you have a very pronounced chemical and spin sensitivity when you do this because of this fact. And very often we use this to do soft X-ray absorption spectroscopy, starting with hard X-rays. Why would we want to do this? For example, when we look at matter at high pressure, right? At high pressure, we cannot go to soft X-rays because soft X-rays will not penetrate the high pressure cells. But if we want to get this kind of sensitivity, we can use this technique here. We come in with a 10 kV or 15 kV, and we look at the emitted photon that has transferred exactly this energy in the sample.
Sorry?
Yes?
Isn't the intermediate state, isn't that a forbidden transition
Sorry?
from an S to a D?
Yes, okay, I was expecting this question. Of course, it's dipole forbidden, you're right. So the probability of going here is not very high. But in the 3D metals, since there's a very large empty density of states just at the Fermi level, you do see these transitions. Of course, they're small, and the edge, actually the real edge, comes from transitions from 1s to 4p. That's the real edge. This is not the real edge. This is a small part at the beginning. So you're right. It's not very probable, but it's there. So normally, as I said, since they're linked, we normally don't do this. We normally have to scan both energies, okay? So you see what we do is we scan the incident photon energy in a little range. So this is here. We're looking at this. See, this is small. This is the 1s 3D. It's very small. This is 4p. This is 3D. We're looking at this very small range. We're in resonant conditions, so the incoming photon is very close to an edge, and they're linked. So for every energy of the incoming photon, we scan the energy of the emitted photon. So I did a little cartoon. So we scan the incident photon energy, and for every energy here, we scan the energy of the emitted photons. And that's how we get this Rix plane. Okay? So if we do not have a detector that allows us to have a very high energy resolution and to see and to scan this, then we measure everything. We integrate everything, all the energies. And so if you integrate in this axis, this is what you get. You see, you lose all these features. You don't see this peak. You lose all this high resolution information. Okay, so the normal absorption spectroscopy integrates in this direction and gives you this little bump. But actually, you have much more information there. And so you can interpret all these features in terms of multiplet interactions, crystal field splittings. You can get information on oxidation state, and so on and so forth. So if you look at that plane from the top, okay, and you draw a diagonal, this is what we call high energy resolved fluorescence detection. Okay, so just to show you the comparison, on the top I'm doing X-ray absorption spectroscopy of two different platinum complexes, okay, one in red and one in blue. And here I'm integrating all the energies of that emission line. I'm taking everything because I don't have an energy resolving detector. I don't have analyzers. I'm just putting a silicon diode or whatever, and I'm taking everything that comes in. And this is what I measure. This is typically the absorption spectroscopy that you measure if you're looking in transmission. Okay, and you're limited by the core hole, which is the core hole broadening. Okay, so it broadens everything. You don't have any structure. You lose it. But if you have an analyzer and if you can analyze the energy and you can sit on a specific energy, then you're looking at this diagonal, and then you start seeing all these features. Okay, so that is really the strength of this technique. So at the SRF, we have two beamlines that do this, one in the soft and one in the hard. ID32, this is the soft X-ray spectrometer. ID20 is the hard X-ray spectrometer. On ID32, they look a lot at superconductors. They look at magnum dispersion, for example, in all these correlated systems with very high resolution. Okay, then we have Raman scattering. So here, what we're doing here is we are coming in with a photon, and we're looking at inelastic scattered photons, where the transferred energy corresponds to an absorption edge in the soft X-ray. So just for an example, we come in with 20 keV, and we measure photons which have an energy of about, let's say, this is 19.5, this is 19. The difference is 540 eV, which is exactly the energy to excite an oxygen K edge. And so actually, this process corresponds to this process. So if we look at the inelastically scattered X-rays, we can see this edge as a function of energy here. We actually see this edge in the spectrum of inelastically scattered photons. And so again, here, this allows us to do soft X-ray spectroscopy using hard X-rays. And it's very, very used, again, in the case of high-pressure science.
But ma'am, we won't always get the exact energy of oxygen KH, I guess.
You can scan. I mean, you can scan. You can scan the energy of the inelastically scattered photons. You have all energies. So if you can measure the energy, you will actually see the edge. The problem normally is that these are, the cross sections for these processes is very small. So you need a lot of photons to see very clean spectra.
Sorry.
Yeah?
So how do you choose the excitation wavelength or the excitation energy?
Yeah.
Do you just want to go as high as possible?
Well, it's a compromise. You calculate a little bit what the cross-section is. If you go too high, the cross-sections go down very, very quickly. If you go too low, then you might have absorption problems. So you find a compromise. Typically between 10 and 20 is a good compromise. So this gives you access also to low Z elements, absorption edges with hard X-rays. You can go and look at the carbon edge, at the oxygen edge. Otherwise, normally you can't do that. And this is a nice example. So this is a mineral that you find inside the earth, in the mantle. And you want to go and see, for example, at the exhausts on oxygen in this mineral at high pressure. You cannot do any high pressure experiment at 500 eV. It's not going to work because the photons will not be able to go through the cell. So you can do an elastic scattering, or what we also call Raman scattering, and you see the oxygen edges there. Okay? Now, with the advances that we've made in these facilities, we can actually get very good data and we can do very sophisticated analysis. Something like 10 years ago, it seemed impossible, but this is now possible. And you can look at all these elements in water, right? Because the incident and the emitted photons are very high energy. They can go through anything, okay? So this is the example of ID20. It's the Raman spectrometer that we have on ID20, which has a lot of crystals, 72 analyzer crystals, because the cross sections are so small. And so this allows you to get nice, clean, inelastic scattered photons, even there in the little tail where you're looking at these edges. Okay, a few words on polarization-dependent spectroscopies. There's many, many different kinds of spectroscopies, and here we are exploiting the polarization properties of the incoming photons. So we have linear dichroism, we have magnetic dichroism, can be linear, can be circular. We can also look at molecules of different chirality, okay, and which absorb photons differently. So you have a contrast between different chirality. If you use circularly polarized photons, I'm going to go quickly through some of these techniques. You have the lecture of Urs Staub, which will tell you more about this. So in linear dichroism, what we're measuring is the dependence of the absorption on the relative orientation between the polarization of the incoming light and the crystallographic axis if you have a sample which is anisotropic. Okay, so the electron density in one direction is different with respect to the other direction. So you have a linearly polarized X-ray that comes in. So you're measuring this direction. So clearly, if you put the sample like this, you will measure a certain absorption coefficient. If you change it, you will be measuring a different absorption coefficient. And that's what you see here. For example, this is the case of cuprates. We're looking at the L edges. In these cuprates, the copper atoms lie on a plane. So if you use an electric field which is polarized perpendicular to the c-axis or parallel to the c-axis, you will see very different spectra. Okay, so actually you're using the photons as a searchlight for the holes in the valence band, because that's where you can go to. You're looking at the available states in absorption spectroscopy. You're probing the empty density of states. And so you can see that when you are probing in the plane, you see these copper available states. Okay, this is circular dichroism, X-ray magnetic circular dichroism. So here, actually, we make the absorption process spin-dependent by using circularly polarized X-rays, because circularly polarized X-rays can transfer their momentum to the photoelectron. And so the photoelectron becomes sensitive to spin. Okay, so it's defined as shown here. This is the case of the L edge XMCD in iron. So the L edge is from 2p to 3d. So the final state is in the valence band, 3d, of iron. So it's the one that contains the information on spin. And so typically these signals are very big. You see very big contrasts. Okay, and then for the L edges in these systems, there are some rules which allow to interpret this different signal in terms of the angular momentum and the spin momentum. So you can actually get quantitative values from this spectroscopy. We can also do this using the K edges. So it's exactly the same thing, except in the K edges, we go from the S states to the P. We don't go directly to D. And therefore, we're not probing the states which contain the magnetic information. But there is, so we do still see a signal. It's a very small signal, but we still see it. And it does contain spin information because P and D states typically have strong hybridization. And so we get the information on the spin also at the K edge. And why do we even bother doing the K edge, given that the signals are very small? Because it's the only way to get information if you want to do experiments at very high pressure, for example, or in environments that absorb a lot. Okay, so that's why people have spent a lot of time. I've done a lot of work in this field with my group. And it's much more complicated to interpret because the information is not so direct. You're not probing the D states. You have to go through all these indirect, let's say, you go through the P, and the P is hybridized with the D, and then you have, it's stronger if you have stronger spin orbit, and so on and so forth. But you can get information on the net magnetic moment on the absorber. You can get information on the sublattice magnetization. You can look at hybridization effects and all this in difficult environments. Okay, now very quickly, photoelectron spectroscopies. So here we come in with X-rays. We're looking at a surface and we detect emitted electrons. And we can look at their energy. We can analyze their energy. We can look at their distribution in angle, so in Q space. Typically, the depths that we're looking at are few tens of angstroms, hundreds of angstroms, because of the low energy of the electrons. There's going to be lectures on this as well on the 1st of April. And then you can look at photoemission spectra and the shape of, you can interpret the shape of these peaks in terms of, you know, the chemical state of your metal. Okay, so for example, if you have an incoming photon, you can retrieve the binding energy of the electron, because this you know. You can measure the kinetic energy of the outgoing electrons. This is the electron work function that you also know. And so you can get information on, you know, chemical structure, molecular bondings, and so on and so forth. You can also look at valence band properties. So for example, this is a case of a system that becomes superconducting below a certain temperature. So you see, at 19 keV, you have this spectrum here. So at the Fermi level, you have a lot of states. And as you go below 17 keV, this drastically drops, okay, because of this opening of a superconducting gap. And then you can do angle-resolved photoelectron spectroscopy, and you can look at the K distribution, the Q distribution, and measure the energies at different Qs. And you can do band structure with these kind of spectroscopies. And you can do also microscopy and imaging, and you can do it in two ways. You can have an optics that focuses on a very small spot, and you can scan the sample on the spot. So this is scanning mode, and then at every position you measure, you know, the electrons, the total electrons that come out. Or you can do it full field. That means you have a large beam that comes in on the sample, and then you have a 2D detector that measures all the electrons that come out, and you can get the same kind of information. And there's talks on this on the 1st of April as well. Okay, so we're a little bit behind schedule, but try to go a little bit faster. Do you have any questions on this? So this was a very, very quick overview of the different spectroscopies, and now we will go a little bit more into detail with X-ray absorption fine structure spectroscopy. So, we start from here. So as I said, to understand EXAFS, we have to sort of, we cannot do it if we're not, if we cannot consider the electron as a wave. So it is a quantum mechanical effect. So you have an incident photon and an ejected electron. If you're looking at this classically, it's a particle with a certain kinetic energy, which is given by the difference between the photon energy and its binding energy. So classically, you would write it like this. Quantum mechanically, you would write it like this, where k is the wave vector of the wave. So you see, you can either see it as an electron, a particle coming out, or as a wave. This blue wave is the emitted wave of the photoelectron. So this wave is our photoelectron, which has a certain wavelength, which is proportional to the inverse of k. Okay, so this is really important. So if you have an isolated atom, you just have this wave that at the beginning, zero kinetic energy is right there, and then it just slowly develops and occupies all space. If you have the absorber surrounded by other atoms, what's going to happen is that this wave will propagate, and at some point it will start interacting with the electronic potentials of the neighbor atoms. And therefore, this interaction can be visualized as, scattering, backscattering of this wave. And these little backscattered waves will eventually reach the origin again. And so, as I said, the absorption coefficient is the probability of a photon being absorbed, which is the probability of the electron being present in the origin. So if you're looking at it here, at the beginning, the electron is here, and then as the energy of this photon becomes higher and higher, the speed of this electron becomes larger, and therefore this wave very quickly occupies all space. And so the density of the electron here decreases very quickly, okay? And therefore, that's why the probability of absorption of a photon here decreases quickly. Whereas here, it oscillates because you have parts of the photoelectron that come back. That's why it oscillates. So we're going to see this a little bit closer. So where do the oscillations come from? So due to a quantum effect, the auto-interference of the photoelectron wave, this blue one, okay, and these little red ones, modifies the probability of this photon being absorbed. Okay, so as the energy of the photon is scanned above the edge, so this is the binding energy of the electron, the kinetic energy is varied. Okay, this becomes greater than 0, and it increases gradually. So K becomes very big as you go away from the edge, but lambda becomes smaller and smaller because it's inversely proportional to K. And the outgoing and the backscattered parts of the wave can interfere either constructively or destructively. And this depends on the ratio between lambda, which is the distance between these circles, and the distance between the atoms. And so this interference actually modulates the absorption probability. And so the frequency of this modulation will give you information on this distance. Okay, and the amplitude of this modulation will give you information on the number and also on the type of electron, of neighbors. So a little cartoon. You see at the beginning you have lambda, which is pretty big because K is very small, kinetic energy is small. So here you have a positive interference. You have a maximum which coincides with a maximum. Then as you go away from the edge, the photoelectron energy increases, which means that the wavelength decreases, and you see the pattern is different. This distance obviously is the same, but the picture that we see here is different because this is smaller. And so we have a minimum because this is destructive interference, and so on and so forth. Then you have again constructive interference, and so on and so forth. So this is the origin of these oscillations. So how do we actually do and practice these experiments? Well, we measure the absorption coefficient. And then we want to isolate the wiggly part, because that's the part that contains the information on the local structure. So we subtract a smooth background, mu0. We divide by the edge step to normalize our signal. And then, since this is an interference effect, we don't want to express it as a function of energy, but we want to express it as a function of K. K is the wave vector. So K is obtained through the definition of the kinetic energy that you saw before. So it's a very simple expression of E minus E0. And this is what we call the Exaf's function. Typically, it is shown as a function of K. And normally, we also multiply it by K squared of K cubed because we want to amplify the oscillations at high K. The reason why we want to amplify them, well, there are several reasons that are useful when we do the data analysis, but this we will see another time. But it's also useful to be able to see when the noise becomes predominant, because that's when you have to stop measuring. It doesn't make any sense to measure if you're only measuring noise. So you see here, the noise is still smaller than the oscillations, so it's still okay. I could have taken maybe a few more oscillations. This is data that I took during my PhD thesis. Then, so here are the Exaf's oscillations. So the frequencies that are contained in the signal, since this is an interference phenomena, give you information on the distance between the absorbing atom and the neighboring atoms through that pattern. And if you do a Fourier transform of the signal, you get what we call let's say, the amplitude of the Fourier transform, it sort of selects the frequencies that are there, and these are actually proportional to the probability of the photoelectron being scattered at a certain distance from the absorber. Okay? So here you see there's a high probability of it being scattered. This represents the electron density at the first coordination shell. This is the first coordination shell. As you go further, you see other coordination shells. So one question is, it looks like there's no atoms here because there's nothing. But actually, it's not that there's no atoms. It's that our photoelectron, remember, in the EXAFS region has a very short mean free path. So it's not going to be able to go very far before it loses energy. The moment the photoelectron loses energy because it has interacted with some other plasmons or other collective excitations or whatever, then it does not contribute anymore to our interference pattern, because by definition, interference is something that occurs between waves of the same wavelength. So if the photoelectron has lost energy, it does no longer have the same wavelength. And so it no longer contributes to the interference pattern. So it's gone. So the intensity goes out. You've just lost it. So the further away you go from the absorber, the smaller is the intensity of the EXAFS. Not because there's no atoms here. It's simply because you've lost the photoelectrons on the way. And they are bringing the information. And here also, it's not because here you have less atoms than here. It is simply because you have lost a lot of information. Okay, so quantitative. How do we get the quantitative information? How do I measure the distance between the absorber atom and the near neighbor? How do I get information on what atom has scattered? Who are my neighbors? So you do it in this way. So typically, it depends on how good you are in sort of resolving your data in terms of individual waves that correspond to these different kinds of neighbors, waves or peaks. So sometimes we talk about waves when we are in Q space. Okay, so you can see it here. Waves, these are the sum of different waves of different frequencies. Or we can talk about peaks, different contributions in real space. And so it depends on how good you are in making a model. So this was stuff that I did during my thesis. I was looking at arsenic, the arsenic K-edge. So that's the arsenic K-edge in one of these systems. And I was looking at this kind of Fourier transform, and I did a fit where I had, in my first shell, I had the 4 indium atoms around arsenic. This is a zinc blende structure. So arsenic is surrounded by 4 indiums in the first shell. In the second shell, it's surrounded by 12 atoms that are a mixture of arsenic and phosphor. So the second shell is shown here. I have 2 peaks. One corresponds to the arsenic-arsenic interactions, and one corresponds to the arsenic-phosphor interactions. And then I was looking at the third shell here, and the third shell is the arsenic, which looks again at an indium which is around this phosphor or this arsenic. So this is the third shell. There's 12 of them. It gives rise to this peak. And then I have other smaller contributions which corresponds to other types of scattering paths. So if you're able to do a model and to identify these peaks, that's how you get your information. So the chi, actually, as you saw, the signal there, these 3 peaks, you can actually write it as the sum of a limited number of contributions. And this is the trick. If you're in the EXAFS region, you don't have to put an infinite number of contributions, because you saw in your Fourier transform we only had 1 big peak and we had 2 smaller peaks. We don't have many peaks. It goes very quickly to 0. And this is what allows you to do a very simple analysis, because you only have to put 1 or 2 or 3 of these. You don't have to put many. Okay? Because EXAFS is very short-sighted. If it had been long-sighted, long-range sensitive, you would not be able to do such a simple analysis. And that's the difference between EXAFS and XANES. In the XANES region, you cannot do this, because your photoelectrons are always there. They can do millions of paths without losing energy, because their mean free path is very long. In the EXAFS regime, it becomes simple. So you can use this approximation because the photoelectron lives very little. So each of these paths, you can write them as the product of an amplitude and the sign of a phase, where the phase gives you the information on the distance. It also has a phase shift, which is, let's say, a signature of the kind of atom that has backscattered. And so the product of the sign of a phase shift and an amplitude factor, which is k-dependent. And this k-dependence is a signature, again, of the atom that has scattered. So in these waves, you have something that tells you what has scattered. Is it oxygen? Is it lead? Is it iron? So you know your photoabsorber, but normally you don't know what is around. But from this, you can identify what is around. So I can look at this, and I can say, oh, wow, this is indium. Okay, I mean, I don't, after a while, you can identify these things. And then you have programs that help you do that. So this amplitude contains this scattering function, which depends on the scattering atom. It also proportional to the number of scatterers. So if you have many, it's going to be bigger. If you have little, it's going to be smaller. And then you have a term which tells you about the disorder. And it defines how fast this signal is damped in k-space due to thermal vibrations and also due to disorder, static disorder. Okay, and then one thing I have to say, you saw those 3 peaks, but you also saw that there were other more complicated configurations like triangles. And actually, the Exaf's equation includes shells of atoms, so first neighbors, second neighbors, third neighbors, but it also includes multiple scattering paths like triangles, squares, and so on and so forth. So in Exaf's, you can have these single scattering paths. You go to a shell and you come back. So these give you the G2, the two-body correlation function, and this is the same information that you get in diffraction techniques, for example, right? Except for here you get it with local, let's say, sensitivity to the very local order, just a few angstroms around the absorber. But you can also have these paths where it scatters twice, okay, but it's still sensitive to the G2. This is a multiple scattering path. You have all these things that contribute, but very quickly, the multiple scattering paths become very small in amplitude. But you see, in some cases, if you can actually identify this signal, or this one, you can get information on the 3-body correlation function. And this is something that you don't get from diffraction techniques. So this is very useful because it allows you to, for example, in disordered systems, to do an analysis on the distribution of triangles, of angles, in liquids, for example. So in theory, you can get information on whatever order distribution function. In practice, if you have very good data, you can go to the G3. Okay, so here's just to show you what the amplitudes look like. So the first shell, you see this is indium. This is the shape. If you go to the second shell, you see the shape is completely different because this is phosphor. So you know that in the second shell, you don't have indium, but you have phosphor. The frequency is also much higher because the distance is bigger. This is the second shell. This is also the second shell. So you see the frequency of this second shell signal and this second shell signal is very similar because these 2 atoms are sitting theoretically on the same crystallographic site. Okay, in practice, it's not exactly. But the envelope is very different because this is scattering from arsenic and this is scattering from phosphor. And then again, on the third shell, we have indium again. So this is exactly the same A as here. You see it has a minimum at around 6, a minimum at around 6. But the damping is much stronger here because this is a much further shell. It's the third shell. So there's much larger damping. And also the frequency is much larger because this is further away. That's the first shell. So that's the lowest frequency.
Sorry?
Yeah?
So these are 4 different measurements?
No. This is the analysis of that initial Exaf's. Okay, if you do a Fourier transform of that Exaf's, you see the different peaks. So if I take that first peak, only that first peak, and I go back to Q space, it looks like this. Okay, if I sum all these, I get my initial Exaf's.
So you pick a range in the real space.
Yes.
And go back.
Yeah. Unfortunately, we cannot do the analysis here. We don't have enough time. But if you are interested, I mean, this is the way that the programs do it. Yeah.
When you say that it's scattered by an atom, it's like by the electron density?
Yes, of course. Yes.
So you have a broadening depending on the spatial extent of the density, or do you see a shift in the frequency because of that?
A shift in the?
Because
Yes, of course. When you scatter, when a wave scatters, it's actually a shift in the wave. There is a shift, and that's the one that I showed you before. Maybe we will come back on it, and I'll show you again. But of course, there's a shift. Actually, here are the phase shifts. So in the formula that I showed you before, we had two places where you could have a signature of the scatterer. One is in the amplitude, so this is the envelope function, this f of k. And then you have also a phase shift that affects the frequency. And this phase shift depends on the scatterer. So these functions is what you need actually to identify your scatterer. You see, they're very strongly dependent on what scatters. So if you have oxygen around your absorber, the EXAFS signal will go very quickly to 0. If you have only oxygen, or if you have only a very light atom like carbon or oxygen, the oscillations will be big at the beginning, and then very quickly they will go to 0. Then you know that you have a light element. But if you have oscillations that have a maximum around, 5, k equal 5, then you know that it's probably something of the order of, Z20, between 20 and 30, like iron, for example. And if you have something which is even more structured, the more electrons you have in the scatterer, the more complex are these functions. Because the electron density that is scattering this wave is complex. If you have only s electrons, like in nitrogen, does nitrogen have only s? No, it has also p, right? Yes, sorry. Well, s and p, you have very simple shapes. But as you go to d elements, then these orbitals become more and more complex. And so the scattering process becomes more complicated as a function of k. And that's why you have all these bumps. Okay, so calculating f and delta. So today we can calculate f and delta from programs. I mean, you have ab initio programs. They calculate the models. You typically give a list of atomic coordinates for a specific structure that you start from. You say which is the atom that absorbs, so what edge you have done. And the program comes up and gives you files for these, which you use then to analyze your data. Okay, simple theoretical description and derivation of the EXAFS equation. Here's where there's going to be a little bit of math, but I think you've already seen some of this. So we want to understand from a math point of view why, if you have a monoatomic gas, you have no EXAFS. And if you have a system which has a lot of neighbors, like an FCC crystal, you have very big oscillations. So let's try to understand from a mathematical point of view why you have such different shapes. So we've already seen this, so I'm not going to go through it again. The important thing is that you see that this matrix element is actually an integral over all space of the interaction Hamiltonian acting on the initial state, transforming it into something. Then this is multiplied by the final state, and then you take the integral of the whole thing. Okay? And that the integral over all space of two functions that are the same, that are perfectly overlapping, is equal to 1. So that's the only thing you have to remember. So we go back, we start from this initial state, go to this final state, and we start from a wave function that contains all the electrons in the atom. This is the initial state. This contains this electron plus everything else. Final state is the same. You have a photoelectron, but you still have many other electrons involved. And you have an interaction Hamiltonian, which is the interaction between the electromagnetic field, which is typically a function of space, and let's say the momentum operator of the electrons. I don't want to go more into details. For those of you who are interested, there's appendixes, and you can go and look at all the different steps. So the first approximation that we do is called the dipole approximation that I've already introduced a little bit, which leads to the so-called dipole selection rules. So it transforms this operator into something very simple. It's just the dot product of two vectors, the polarization vector of the X-rays and the position vector of the electron. What is this dipole approximation? It simply says that the wave that comes in, so these are X-rays, so the wavelength is typically an angstrom or so, has an amplitude which is practically constant in the region of where the photoelectron, the core electron is, because the core electron is sitting very close to the nucleus. So its extension is of the order of 10⁻⁵ angstroms. It's very, very small, very localized at the nucleus. And so when the X-ray come in, the amplitude of this X-ray wave is practically constant here, because this wavelength is 1 angstrom, is 10 to the 5 bigger than its actual localization. So this is what the dipole approximation says. So you see, I get rid of the R dependence, and it just becomes a constant. Okay, so that's the first one. Then we go to the single electron approximation, which, what does this say? It just says that this electron here does not really interact with all the others. So I can factor all the others out. And the same I can do in the final state. So the photoelectron does not really interact with all the other electrons. It does its own thing, and so I can factor all the other electrons out. That's what the single electron approximation says. And finally, the sudden approximation. What does that say? It says that I can actually take all these other electrons out of the matrix element, because the interaction, the photoexcitation does not really involve them that much. I mean, of course it will change their energies, because I'm creating a big core hole there. So all of these electrons will have to readapt to a different potential, because they see, since there's a core hole, they see an additional positive charge, right? So all their energies will be perturbed. But this does not happen immediately. So I can get rid of them from this matrix element. Okay, so I factor them out and I call them S0 square. And S0 square is this overlap of the initial and final states of all the other electrons. So remember, this is the integral over all space of the product of these functions. If this function here and this function here are identical, what does this mean? This means that all the electrons that are not participating, if nothing happens to them, that means that their state is identical before and after. This is equal to 1, right? Because the integral over all space of two functions that are identical, they overlap perfectly, this is equal to 1. So S0 square in the best of cases can be 1. In reality, it's never equal to 1, because they do change a little bit, because their energies change and they change a little bit. So this is a number which is close to 1, but it's never equal to 1. It's typically around 0.8, 0.9. Anyway, we get rid of it. And so at the end, we remain with just this matrix element here. Okay? So we have this matrix element. Okay, again, there's Guillaume's talk that will tell you more about this. I would just want to say one important thing. These wave functions actually can be written in terms of a spin component, radial components, and angular components. And these are mutually independent. They don't really talk to each other. So you can factor out this matrix element into the product of 3 matrix elements. Now, what happens is that here, many of these are 0 because of this very simple dipole operator. And that's how we get the famous dipole selection rules. Only a few of these final states, a few of these actually contribute to these transitions. All the others are 0. The only ones that contribute are the ones that link the initial and the final state through these relationships. Okay, so that's where the dipole selection rules come from. And so again, I'm going to repeat it again. If you're looking at a K-edge, you're starting from a level S, right? You're exciting S, that's your initial state. That means L equals 0, which means, according to the dipole selection rules, that you can only excite to a P state, a state of P symmetry. If you go, for example, to the continuum, it's going to be a state of P symmetry in the continuum, and so on and so forth. Okay, now we go back, and we have to calculate this. Okay, so remember, this is the polarization of the X-rays, this is the electron position. And we have applied these approximations, and if you want to learn more about these, you can go and look at the appendixes. So this is the initial state of the core electron, and this is pretty simple. We know how to calculate. This is the ground state. We know how to write this wave function. However, psi f is much more complicated. It's much more complicated because we don't know how to write that wave function, because it depends a lot on the details of the environment, on the energy. This is the photoelectron. Okay? So how do we solve the problem? Well, let's start from the case of the isolated atom. When do we have to stop? 3 3:30?
40.
Ah, now. Okay. So let me just finish this and then we go for coffee. So isolated atom. So we write psi f as psi f 0. This 0 means that we are looking at an isolated atom. We don't have anything around it. So what do we have? Psi f is this blue wave I told you at the beginning. Remember, you can see it as a wave. You can see it as a particle, but we want to see it as a wave that goes out. So we just substitute psi f with psi f 0. We put it in here. Okay, and now we have to calculate this. So remember, this is the integral over all space of this function multiplied by this, modulus square. And what is this? Actually, yeah, it's the overlap integral of the initial and final state wave functions, and this is something that monotonically decreases as a function of energy. There's no oscillations here. Why? And I did a little cartoon to try to explain this. At the beginning, this is your initial state wave function. It's something which is localized in an area of 10 to the minus 15 angstroms around the nucleus. So it's really, really small. Everywhere else in space, this function is 0. What does this mean? This means that in this integral, the only part which contributes to the integral, because you're integrating everywhere in space, the only part which will not be equal to 0 is the part where this function is not equal to 0. That's the only thing that contributes. Everywhere else, you don't care. So you don't care what this looks like everywhere in space. The only thing that you care is what this looks like right there, where it overlaps with here. So if we start from here at the beginning, the final state wave function is identical to the initial state because the electron is still there. Okay? As you go to higher and higher energies, the photoelectron gets more and more kinetic energy. And so if you imagine it as a particle, it can move very fast. It can occupy a big, big space. So its wave function flattens out because the integral over all space is equal to 1. So obviously, it must go down at the origin because it's occupying a very big space. So the probability of finding it at the origin where it overlaps is very small. So this overlap goes down monotonically. Okay? And just because we are there, if we are in a non-isolated case, you write this as this blue wave plus the backscattered wavelets. These are the red wavelets that come in. So we take this function, we introduce it into our matrix element. So we take this. So we take the outgoing wave, the blue wave, we add the scattered wavelets because now we have neighbors. We get this, we write the integral because you know now how to do this. We have already done this. We write the integral, we develop it, all the things. And what do you see here? You see this is a square of delta, very small. These are very small corrections. So this we throw away because it's too small. This we have already seen in the previous slide. This is exactly our mu 0. Okay? And this is what gives you the exafs. Okay? So this you have, you see, you have something that looks like these little wavelets, but calculated in the origin, again. And here you have the blue curve, again, calculated in the origin, because psi I is different from 0 only at the origin. And so this is the last slide before coffee. If you reorganize all that, this is mu 0 on the bottom, because that's the definition. What do you see here? You see that the exafs, these oscillations, are given by the interference between the outgoing wave function and the backscattered wavelets, but only that portion of these functions that is in the origin. Only that region counts. So that's why we don't really need to know what these functions look like. And that's why it's easy. So the dominant contribution to the integral comes from the spatial region close to the absorber atom, where the core orbital wave function is different from 0. And this is, oops. So the region where psi I is different from 0, 10 to the minus 15, close to the nucleus, represents the source, because that's where the core electron comes from, and the detector, because that's where you're detecting the exafs through these integrals. Okay, for the photoelectron that probes the local structure around the absorber. So this is the origin of these oscillations. Okay, we stop here, we go for coffee, and we come back like at 4:15 or something. You have half an hour?
20 minutes.
Oh, okay. So we come back at like 4:05.